Hi everyone, welcome to my presentation. Sorry I couldn't give it on Friday. Um, the protein that I would like to show you is called PARK7, and it's also called DJ-1. And it's called PARK7 because it's one of a group of genes that was discovered to have some kind of connection with Parkinson's disease. In the case of DJ-1, mutations in this protein lead to recessive inherited Parkinson's disease. Um, PARK7 is a deglyoxylase, which means that it catalyzes the conversion of glyoxyl into lactate. So one particular glyoxyl that is found in the body is methylglyoxyl, which is an intermediate of glucose metabolism and other metabolic processes. It's actually quite poisonous because it can bind to lysine or arginine on proteins such as collagen, and when you get a lot of these glycation events occurring, the collagen loses its structure. It's also found, or methylglyoxyl is also found to bind to histones and disrupt their function. So DJ1 is seen as a very important enzyme in making sure that those events get cleared away. Here's what it looks like. So the crystal structure that I found is of one subunit, but in the wild, DJ1 exists as a homodimer. On the left here, I've colored the protein by residue type. So on the inside, you can see the white hydrophobic residues forming a beta sheet, and this is all surrounded by alpha helices, and some of these are basic or acidic. The homodimer has a 180-degree rotation, so if you look at this alpha helix over here, that's that same one down over there. This crystal structure actually shows DJ1 bound to a synthetic substrate called glyoxylate. So here's methylglyoxyl. So there's the methyl, and then this is called glyoxyl. This is the typical substrate of DJ1. But if you change this methyl into a hydroxy, and then you also make this into a carboxylic acid, and you get glyoxylate, it will bind to the catalytic site in DJ1, but it will not be released. So this is a great synthetic substrate to use if you want to look at the structure of the protein bound to the substrate. And as you can see, there is here's the binding pocket. And I'll show you actually in the next image that it's actually quite exposed to solvent, so it's not a very deep pocket. Yeah, here it is. So the substrate is actually bound by the cysteine over here, and the binding pocket is kind of far out in the in the protein surface. Unfortunately, they only have a structure of the protein bound to the substrate, so they don't have one without. So I couldn't really see what the difference between the two, like bound and unbound, is. But they also have a structure of, oh, this is human DJ1. They also have a structure of DJ1 from Arabidopsis, I think. And they have bound and unbound for that. And the interesting thing that they noticed from that is that the conformational change between bound and unbound is very slight. There's not a lot of movement. So anyway, so the substrate comes in and it's bound by this cysteine 106. And one of the mutations that has been found to be correlated with Parkinson's is cysteine 106 to a serine. And if this mutation occurs, then the enzymatic ability of the protein is completely removed. So this is a functional assay that involves a synthetic substrate that's a hemithioacetol, and they just look at the absorbance at this particular wavelength. So in wild type, you just see it see this substrate getting eaten up, but then with the mutation, nothing really happens. Another mutation that has been discovered to cause disease is if you take this leucine and it's converted into a proline. So if this mutation occurs, then the functional ability of the enzyme is completely gotten rid of. So you can see it's almost completely the same as the cysteine 106 mutation. And the reason for that might be because if you disrupt this alpha helix over here, you're interrupting the protein's ability to first of all form as a subunit, but then also form as a dimer. And it seems like this is very important for the enzymatic function of the protein. I found this interesting experiment over here. This is a yeast-2 hybrid experiment, so just looking at which subunits are binding to each other. So here's DJ1, wild-type DJ1 binding to wild-type DJ1. If you put, and then here's the mutated form, it will not form a homodimer. But if you take one wild-type DJ1 subunit and then one subunit that has this L166P mutation, if you put them together, they will actually form a heterodimer. So this would maybe be an interesting thing to look at if, I'd be kind of curious to see if this heterodimer actually has any kind of functional ability, because that might say something interesting about is there a relationship between enzymatic function and the dimerization. And this is another interesting mutation where this glutamate, which is on the solvent exposed side, is mutated to an aspartate. So just to remind you, these two amino acids are very similar to each other. There's just a one kind of methyl difference over here. And this mutation doesn't seem to have any effect on DJ1's typical enzymatic function. So in this functional assay, there's a little bit of a difference, but maybe it's not significant. And yet, when this mutation occurs, there's some kind of disease mechanism that's associated with it. So the paper that first reported this mutation did a molecular dynamics simulation on the surface of the homodimer and found that the electrostatics of the homodimer are impacted by this mutation. So maybe something's going on where DJ1 isn't able to bind to other proteins, so it can still do its function, but it's not being told where to go. So I thought this was an interesting example of how you can mess up a protein in a very mild way and do it in a part that's very far away from where the catalytic action is occurring, and yet you can still cause some negative consequences. So thank you for listening to my presentation. If you have any questions, you can send me a message or ask me in person. And yeah, thank you for watching my video.